So today we'll get started. We're going to talk about logarithms being inverses, which we've mentioned that already. We're just going to formalize some things today. Like we've done a lot of this already, but really just really repeating it, making sure we're comfortable with all this material because there's a lot. First thing, the definition of a logarithm. It follows that the logarithmic function g of x equals log base b of x is the inverse of the exponential function f of x equals b to the x. And what that means, if we compose these two functions, when you have inverses, g of f of x, you should get x. And remember, we did this on our first graded assignment even, where we said, oh, well, if you have a function and its inverse, and you compose the two, you're going to get x. And that's exactly what we're seeing here. And then we have a function and its inverse, and we get x. And now what happens in the middle, we have this log base b of b to the x power. So, I mean, if we think about that, this can be rewritten as x times log base b of b, which you just drop that exponent out in front. And then log base b of b is just 1. We saw that on the warm-up today. And then you're just going to be left with just the x value, which is exactly what this is showing here. Similarly, what we've talked about is if you're solving algebraically, I've mentioned if you take a base of both sides, in this case like base b of both sides, this part equals 1, and this x kind of drops out in front. So you're going to have like x times b log of b, and the b log of b becomes a 1, so you're going to be left with just the x. All right. So we've already talked about that. We've done that a couple times now on those solving equations, but now we're just kind of formalizing it and saying this is exactly what it is. On our examples today, first couple examples, I have 10 log of 4, and because there's no base written there, that's just assumed that it's a base 10. So essentially what I have is I have 10 log base 10 of 4. So when this simplifies, I'm just going to have 4 left. That's really what's happening with that example there. On the second example here, log base 5 of 25 to the x power. First thing I can do is I can drop the x out in front. So x equals log base 5 of 25. And now, since I have log base 5 of 25, what I have to do is I have to try and match the base and the other number. And that's kind of a weird way to say it. But I want the 5 and the 25 to be the same number. So since the base is 5, I can't change the base. I want 25 to be rewritten as 5 to a power of something. And that's going to help me simplify this a little more. So in this case, if I just go to my calculator and I try 5 to the first power is 5, 5 to the second power is 25, hey, I could actually rewrite 25 as 5 squared. That's the exact same number. 25 is 5 squared. And once I have that, I can write the 5 squared over here, and this 2 is just going to drop out in front, so I have 2x times log base 5 of 5. Log base 5 of 5 is just 1, so I'm going to be left with 2x. And that's simplified for this example. Okay, that's the idea. All right. Now, finding the inverse of each function. This is the one thing we haven't really talked about yet with these finding the inverses from logarithms to exponentials. We've talked about changing forms a little bit, but we haven't done straight up practice of finding the inverse. So first thing I want to do whenever I'm finding an inverse, swap x and y. So this first problem, I'll rewrite it as x equals 6 to the y power. And then the next step, I'm going to solve for y. And when I say solve for y, I mean, there's really two methods I can do there. The first method, all right, method number one, is I can change forms. So I have this x equals 6 to the y, and I can remember, oh, well, this becomes log base 6, and I solve for exponents, so I'm going to solve for y equals x. That's the change forms method. The other method we can do method 2, we're going to say let's log both sides. Just like we did when we were solving last time. And if I log both sides, I'm going to get, in this case, I'm going to choose log base 6 specifically. Log base 6 of x equals log base 6 of log base 6 of 6 to the y power. Anyone know why I chose log base 6 specifically to use here when I logged both sides?
Because when you log both sides, that 6 is just going to be log of 6 of 6, which is just 1.
Exactly. I chose the 6 on purpose. That was an intentional choice because I have a log base 6 of 6 here now, and that just becomes a 1, so I'm left with y equals log base 6 of x. If I did that with a log base 10 or a natural log, then I'm going to end up with some kind of nasty equation on the other side. I can do it, and I can still solve for y, but I chose log base 6 because it's going to save me some steps and some time. So specifically chose that one on purpose. Okay, so those are the two methods you could use for finding an inverse of a function. Excuse me, one more problem here. We'll do y equals natural log of x plus 3. So the first thing I want to do is switch x and y. X equals natural log of y plus 3. And then I have natural log, so natural log is like log base e. So I want to do base e to both sides. E to the x equals e natural log of y plus 3. And this right here is like a 1. So I'm left with e to the x equals y plus 3. And then I can subtract 3 from both sides. E to the x minus 3 equals y. And that minus 3 is not part of the exponent, it's just below. That's e to the x power, and then minus 3. And that's our inverse for this one. That's the one method I can use, is the base e on both sides. The other method I could do is the change forms method, where I just say, okay, x is the exponent, so I'm going to go from natural log to e, and then x is the exponent, I put x there, and I have equals y plus 3. And then I would still solve. Both methods work. Both methods are equally effective. Just your choice of which method you prefer, really, there. And as long as you're showing your work with one of those methods, that's all that matters to me. Okay, now I've got 6 problems here. I'm going to give you guys about 10 minutes to work on these 6 problems. Actually, we might not need that much time, but I'm going to give you guys a few minutes to work on these 6 problems. Number 3, specifically, when you're doing that one, think about, how do I rewrite 64 as a 2 to a certain power? That's the trick for number 3. So think about how to rewrite 64 as 2 to a certain power. Try those 6 problems. So now that we've looked at those 4 problems, the last thing I want to look at today, just a couple examples of solving, so a little more solving practice. The first example, I'll zoom in on, log base 2 of 4x equals 12. So to solve this one, the first thing we're going to want to do is go ahead and take a base 2 of both sides. Or you can just change forms if you're more comfortable doing that instead. So we're going to get 2 log base 2, 2 to the log base 2 of 4x power equals 2 to the 12th power. This 2 log base 2 is going to become like a 4x times 2 log base 2, and the other side is 2 to the 12th. So we get 4 to the x, or 4 times x equals 2 to the 12th is like 4,096 when I put that in my calculator. I divide both sides by 4, and I get x equals 1,024. Once I find that answer, I'm just going to go back and check. And to double check it, I just need to plug in 1,024 into this problem. And I should get log base 2 of 4,096. If I did it correctly, 4,096 should be, should be 2 to the 12th. And I can plug that in my calculator to check. I could rewrite this in a different form to check. But if it's 2 to the 12th, then the 12 drops out front. I get log base 2 of 2 equals 12. And I get 12 equals 12, which checks out, so that is the correct answer. Another way I could put it in my calculator, when I get to log base 2 of 4,096, I do log of 4,096 divided by log of 2. That change of base formula would help me put that in my calculator as well. But really important that whenever I find my answer, I check my answer as well. Part B, 5 to the x equals 120. So I'm going to start by logging both sides. And for this one, I'll go ahead and say, let's do natural log of both sides. Natural log of 5 to the x equals natural log of 120. Now, the x can drop out front because it was an exponent. And I just want to get x by itself. So I'm going to divide both sides by natural log of 5. So x equals natural log of 120 divided by natural log of 5. I can put that in my calculator now. And x equals approximately 2.975 something, so we'll just say 2.98. And again, if I were to put that into my calculator to double check, I'm just going to get the answer real quick. Natural log of 120 divided by natural log of 5. 2.9743 or 46. So actually I'll make it 2.97 instead of 2.98. It's terrible rounding, but it's 2.974. And if I put it in my calculator to double check, when I check it, I want to put in 5 to the 2.97 power. But if I can say as much of it as possible, yes, what's your question?
Oh, why'd you use natural log instead of normal log?
You can use whatever log you want. That's the beauty of when you're doing anything to both sides, you can do whichever one you want. If I did normal log of 120 divided by 5, log of 5, I'm going to get the exact same answer. Notice that, like, can you see that in my calculator? It might be a little dark.
Oh, we can't see.
Can't see it, dang. Okay, but I got 2.974635869 from one method and 2.974635869 on the other method. So they're the exact same number. It doesn't matter which method I use. I can use whatever log I want. So on this one, I just decided to show you with the other log just because.
Okay.
To just prove that you can do it with either one. So when you're checking, you put this whole big number in equals 120, and you should get 120 equals 120. So this one checks out. So B works as well. All right, last one, part C. log base 2 of x plus 2 plus log base 2 of 5 equals 4. So you got to be able to consolidate the logarithms, condense, I should say. So log base 2 of 5 times x plus 2. And I should get log base 2 of 5x plus 10 equals 4. And now I can do base 2 to both sides. Because this was a log base 2, that's why I chose the base 2. And I get 2 to the 4th power on the other side. So 5x plus 10 equals 16. That's 2 to the 4th power. And then I'm going to just simply solve for x. Subtract 10 from both sides. 5x equals 6. Divide both sides by 5. And I get x equals 6/5. And then I can go back and double check that one. And it does indeed work. I get 4 equals 4 when I plug it back in. So I'm just going to leave it at that. I'm not going to show the check for this one. All right, but we got about 7 minutes left in class. 3 more problems I want you guys to practice right now. Notice that there's a lot of these ones where I have you condense 2 logarithms. It's very likely you'll see something like that on the test. So if you struggle with those types of problems, start with number 2 and try that one right now, and we can look at that one together as a group in a second here. Okay? And I'll put the answers up in just a second as well. Mm-hmm.